1.8 times that among the non-traditional group. But let's suppose we took our data of these 468 people and divided them by sex and got the following two subsets. Let's suppose this is what happens to the females in our data set. Let's suppose that half of our traditional group were women. So half of the 86, 43 of them were women. And let's suppose that 84% of the integrated group were women. So is different. Half of the traditional group are made up of women, but 84% of the integrated group are made up by women. Let's suppose these women, 43 people in the traditional group, let's suppose 4 of them had diabetes and 39 don't. So the prevalence among them is 9.3. Among the integrated group, let's suppose 30 of them have diabetes. Their prevalence is also around 9.3. So among women, they have essentially the same prevalence, 9.3 in the traditional group, 9.4 in the integrated group, the 2 decimal places. Now the prevalence ratio is only around 1.99 among them. It doesn't matter what group you're in. If you're a woman, you have the same prevalence of diabetes. Likewise, let's suppose we look at the males, the remaining people in these studies, the remaining half of the traditional group, the other 43 people. The remaining, this is a typo. This is not the 320. This is the remaining 16%. And of those 16%, 29 of them were diabetic and 33 of them were non-diabetic. So all I've done in this slide, if you want to correct this typo, is I've gone back to the women's, slide, looked at in the previous slide, subtracted this slide from the original slide that had everybody in it, and that would give me the slide of men. The only wrong number here for the men should be this total. It's not 320, it should be, 62. But now, among men in the traditional group, or among men in the integrated group, about 46% of them are diabetic. That means the prevalence ratio, again, around 1.99. So why are we getting different answers? When we look at only men, prevalence ratio around 1, or only women, prevalence ratio around 1, and when we looked at men and women together, we got a prevalence ratio of 1.8. What we had here are two groups of people, traditional and integrated, that differ from each other on 2 points. These 86 people are traditional, and these 382 are living an integrated lifestyle. But these 86 people are also made up of 50% men and 50% women, while these 382 people are made up of 80-something, 84% women and only 16% men. So the sex distribution is different in the two groups. Also, the prevalence of diabetes changes with sex. It's around 9% if you're a woman. It's almost a half if you're a male. So what we saw here in that first table is an example of confounding, in this case, by sex. The two groups we're comparing, traditional and integrated, differ with respect to their sex distributions. The prevalence of diabetes increases when you move from females to males, from 9% to 43%. So gender is satisfying 2 criteria. In terms of that diagram that we looked at before, and now in this case, gender is related to the exposure, what lifestyle you have, and the fact that people in the traditional group are half men, half women, but people in the integrated group are mostly women, 84% women, 16% men, and gender, the prevalence increases when you move from females to males. So as a result, again, we have confounding. And as a result, the crude risk ratio, prevalence ratio 1.8 is misleading. Prevalence ratio should be around 1, because that's what we saw when we had only men in our study or only women. So how do you identify and control for confounding? What I was just showing you was an example of stratification, where I essentially took our data set and divided it into 2 groups. Men only did analysis among men, women only did analysis among them, and saw what the answers were for men and what they were for women. This is one way of trying to control for confounding. The more common way is what we're going to be talking about in the coming weeks when we talk about biostatistics using outcome models. And maybe if we have chance, we'll talk about another type of regression model known as a propensity score, which is another way of controlling confounding or talking about confounding. I think I'll skip over the stratification slides and skip over the regression slide. Now, how can you avoid confounding in a study? Well, in an experimental study, you can try to avoid confounding by randomization. These types of studies are limited to experimental studies, limited to situations where ethics allow you to do a study. But what does randomization buy you? When you flip a coin and you assign people to groups, depending whether the coin came up heads or whether it came up tails, the coin doesn't care how old you are. The coin doesn't care whether you're a male or a woman. You would expect when you flip a coin that half of the women will be put into one treatment group and half the women in the other treatment group. Half of the men in one treatment group, half of the men in the other treatment group. So from randomization, you would expect the same sex distribution in your two treatment groups that you're going to be comparing. You should expect the same age distribution. Therefore, none of these factors, age or sex, none of these potential confounders will meet the first definition of what a confounding factor has to have, meaning it's not going to be related to your exposure. Two groups you're comparing, the exposed and the non-exposed, treated and the non-treated, by design, because you randomize people, are going to have the same distribution. Sex or age cannot be the reason why one treatment group has different outcomes than the other treatment group. Because both treatment groups have the same amount of men, both treatment groups have the same amount of women, both treatment groups have the same amount of old people and young people. They can't be the reasons why you had different outcomes in the two groups. So in experimental studies, randomization is a way to avoid confounding. Other ways you can avoid confounding in non-experimental studies is to restrict your study to only men. Only enroll men in your study. Compare men who are exposed to men who are non-exposed. Gender cannot be the reason why the exposed people have different outcomes than the non-exposed people. The problem with restriction is you don't have any women in that study. So from your study, you're not going to be able to tell me anything about the effect of the exposure among women. You've limited your generalizability to only having a study with men. You've avoided confounding by gender, but you haven't been, but the price you've paid is you no longer can talk about the effect of your exposure among women because you have no women in your study to measure its effect. A type of restriction is matching. Matching restricts who gets into your comparison group. So let's suppose I'm doing a cohort study. I want to know whether smoking causes heart disease. I'm worried about confounding by age. What I could do is I could enroll a smoker in my study. Ask them how old they are. If that smoker says he's 42, I go out and find a 42-year-old non-smoker. If the smoker was 88, I find an 88-year-old non-smoker. I match my non-smokers to my smokers by age. But at the end of the day, when I've enrolled all my people, average age of my smokers is going to be the same as my average age of my non-smokers. There's going to be no association between age and smoking status. Yep. And age cannot be a reason why I have different outcomes in my smokers and my non-smokers, because my smokers have the same age distribution as my non-smokers. So these are the three ways you can avoid the potential for confounding in the design. In the analysis, the way we control for confounding is either through stratification or generally through modeling. Modeling is what we'll be talking about in a few statistics. So let me just end today by talking about one last concept called effect modification. Effect modification is sometimes confused with confounding because, like confounding, it can be detected by using stratification. But what it does, it refers to an entirely different concept. It refers to the exposure of interest or your treatment of interest having different effects in different subgroups of people. So what it involves is doing subgroup analyses, dividing your data set up into subgroups.